in the last class you saw how that equation F is equal to KBIL sine theta came up, right? Through the experimentation. So you saw how force could be investigated with magnetic field strength, force could be investigated with the different currents in the conductor, how the force can depend on the length of the conductor. How do you change the length of the conductor in that experiment? How do you change the length of the conductor carrying current? You know the experiment I'm talking about, right? The two rails like that, and the conductor sits, yeah.
You spread the
spread the railings. If you spread the railings like that, you are actually having more current carrying segment, right? So you have more current carrying area, the length. So that's pretty. It's not the whole length of the conductor that matters. From where to where is the current actually flowing? And the other factor that you saw there was the angle. So if you have this conductor, if you keep it like this, then the conductor's length is from here to here. But if you keep it like this at an angle, if you keep it like that at an angle, although it looks like pretty long from here to here, how much is the actual length seen by the magnetic field? Okay, how the magnetic field looks at it, that's more important. So, like, how much of this marker, how much of this do you see now? All of it? Why? Because you're looking perpendicular to it. If I do it like that, how much of the marker do you see now? Only that much. Only that much. You're not seeing the whole marker. You're only seeing that much, which is basically the sine component of the length. Make sense? So when the length is like this, and the magnetic field is acting like this, what the magnetic field looks at is only this much. So this is the length, this is the angle theta, this is L sine theta, and that's why you have this coming out. Make sense? In fact, these are together. But you can investigate them independently. But they are actually together. You can see when the length changes and the angle is present, the L sine theta is what matters. L sine theta is what matters. So the length of the conductor in the eyes of the magnetic field will change. Okay? The same way as how much of the moon do you see? What's the area of the moon that you see? How much is the area of the moon that you see? How much? Tell me an equation for that. You all know. What's the area of the moon that you see? 1/2 what?
1/2.
Surface area of a sphere should be all known to you. That's the volume. 4 pi r square is 4 pi r square is the entire surface area of a moon. So how much do you see? You only see pi r square because you don't see a sphere there. You just see a circle. You don't really see a sphere. Do you see a sphere? No. Your eyes are intercepting only that, which is basically pi r square. Your eyes are only intercepting pi r square, not 2 pi r square. You don't actually intercept all the sides and all that stuff. You don't see that. Your eyes are kind of intercepting only that circle. So instead of the moon, if it was a disk kept over there, you'll still say it is pi r square. You get it? So how much you intercept? That's exactly what it is. But if I give you a basketball and show it to you like this, how much area do you see? Then what? Pi r squared? If I hold a basketball right in front of you and say, all right, how much area do you see? It's tough thing to say. You can't say 2 pi r squared. It's tough because this time now you are actually looking at it with 2 eyes. That means there's a depth of perception. Like you're looking from this angle, you're looking from this angle, so you are seeing the ball in a three-dimensional format. And so you cannot specifically say it is either 2 pi r square, but it's definitely not pi r square. You see more than that. You see much more than that. Because it's, now, if I close one eye, then you'll see a circle. The basketball will look like a circle after you close one eye, because one eye means like you're just intercepting only that. Make sense? Remember last year we were talking about the stereoscopic vision. Well, we didn't talk about it. With one eye, you lose that 3D perception completely. With one eye, you lose the 3D perception completely. You only see 2D. So, can you play football with one eye closed?
Nope.
It'll be terrible. It'll be terrible. With one eye closed, you don't have a depth perception. You'll be totally lost as to where the thing is. All right? So, even if like you want to throw the ball to someone with one eye closed, you won't know where he is. How can he throw? You know, you see the person, but how far is he? You can try it out. You can just close your eyes and see like any object. You cannot guess the distance. But with both eyes open, you can actually see the distance, and you can almost say, all right, that must be around so many feet. You can almost say like this many feet and so on. Well, on a football field, of course, you know, it's different because football ground, right? You say field or ground? No. What do you say? Football ground or field? Field. Soccer what? Soccer field. Soccer pitch. Cricket pitch. Cricket ground. Soccer is what? Field or ground or what?
They call it a field.
Pitch. Why is it pitch there?
It's English.
It's like you lace up the boots to go on the pitch.
You don't really pitch it. K is equal to 1. We will also see what K is and how K is 1 and all that even in the next chapters, because we will still be talking about K. But here, K takes a value of 1. You can write it down. K takes a value of 1 through the definition of the Tesla. K takes a value of 1 through the definition of the Tesla. So what is the definition of Tesla? You can write that down. The magnetic field is said to be 1 Tesla. The magnetic field is said to be 1 Tesla. The magnetic field is said to be 1 Tesla. When a conductor of length 1 meter, carrying a current of 1 ampere, placed perpendicular to the magnetic field. Placed perpendicular to the magnetic field, which means at 90 degrees. So sine 90 becomes 1. Again, B is said to be 1 Tesla. If a conductor of length 1 meter carrying 1 ampere placed perpendicular to the magnetic field experiences a force of 1 Newton. So that magnetic field is called Tesla, 1 Tesla. So if you put 1 for all of them, K automatically becomes 1. So B is measured in Tesla. Symbolized by just capital T. So you'll be saying, all right, the magnetic field strength is 5 times 10 to the minus 3 Tesla. What does that mean? That means 1 meter, 1 ampere perpendicular experience a force of that much. That's why K takes a value of 1, and from here onwards we'll say F is equal to BIL sine theta. Now if you're looking for the maximum force, then it is BIL. The maximum force is simply BIL, because then you're looking at perpendicular options. So when the current and the magnetic field are perpendicular to each other, then you get the maximum force. But if the angle reduces, then the force reduces as well. When the angle is 0, sine 0, 0, so the force becomes 0. So when the magnetic field and the conductor are placed in the same direction, there is no force expected there. All right? F maximum is BIL. The other one is force on moving charges. Force on moving charges. So let's go to that one. Let's say that's a conductor carrying a current. That's a conductor that's carrying a current in that direction. That's a conductor carrying current in that direction. And placed in a magnetic field into the board. The conductor is placed in a magnetic field perpendicular into the board. Which way does it experience a force? Upward. Current, magnetic field, upward. Fleming's left-hand rule. Try to use just Fleming's left-hand rule. You may have other rules, but then, you can get confused with that. Especially, okay, in this chapter you may not get confused much about any other rule. You can use anything you want. But when you go to chapter 21, the confusion will be doubled. Yes.
Is it like still making the right-hand rule field?
Yeah. All those things are still, which one? The field on this one?
Yeah, like the current is the conductor still.
Yeah, this conductor has its own field this way.
Yeah.
This is a different field, and this one's field is a totally different one, and the interaction between this field and this field is what causes the push.
Does that mean that the field on top is weaker than the field on the bottom? Because like
Yes.
that was going down.
Exactly. There's more crowding down here. So it's going to be this way. It's going in this direction. Right? So, okay, so that's a conductor that's carrying current and it's going to experience a force upward. Yeah. And the force is BIL. We're looking at perpendicular. Okay. But now let's look microscopically into it. This current is mainly because of the electrons going the other way. Electrons are moving in the opposite direction. If the current is that way, the electrons are drifting in this direction. And you've come across that word drift. Electrons are drifting in this direction. That is what constitutes a current in that direction. And let's say there are n electrons in this conductor. Let's say there are capital N number of electrons in this conductor. So what really is happening is that this force experienced by the entire conductor is all because of the electrons moving this way. Right, Frederick? So if the electrons are moving this way, that is what causes all this force. So this force is the force on n electrons. That's a force on n electrons. Yes, it is a force on the conductor, but the conductor has n electrons, and it is the electrons which are actually like creating all this creation of force. And therefore, The lesser the number of electrons here, you're going to have lesser forces coming in. Okay, so this is on, if this is a force on n number of electrons, BIL. And so, taking it from there, on n electrons, the force is BIL. Now, what is I in terms of V? What is it? This is called the drift current. If you switch your pages backwards, you will see the equation for drift current. Yes. B N A E V, and then the L. So this is the equation for drift current. We already seen it before. N A E V. A is the area of cross section of this wire. E is the charge of the electrons. V is the drift speed, how fast it's moving. What is N?
Number of electrons. Electron density.
Electron density, which is what? Number of electrons per unit volume. This is the number of electrons per unit volume. If the length of this conductor is L, that's why this L is there. And if the area is A, the volume of this conductor altogether is AL, and there are n electrons. So I can replace this n, I can replace that n with n over AL. This is number of electrons per unit volume, like electron density. And this is the number of electrons here in this case, and AL is the total volume, so we have this. And then I'm going to put all of the other things back. And you can see there, area cancels off, length cancels off. So you end up having force on n electrons, B, N, E, V. That's a force on n electrons. So what's the force on an electron? If the force on n electrons is B, N, E, V, what's the force on one electron?
B, E, V.
B, E, V. The force on just one electron is going to be BeV, where B is the magnetic field that this electron is subjected to when it's moving at the speed of V, perpendicular to the magnetic field. Now, if it is not perpendicular to the magnetic field, then you have the sine theta sticking along with it. Right? If it is not perpendicular, you're going to have sine theta here. So this is something that can come in if the angle is not 90. Okay? In general, I can write down force on any moving charge is equal to B, Q, V, sine theta. That's the general equation. Force on any charge Q is going to be B, Q, V, sine theta. And what's the maximum force? It's going to be B, Q, V. B, Q, V.
This is the homework that I said.
Probably a trace of it should be there. But when you're given a homework, you just have to go back. Do you open the e-text at all? You should. Just go back and read something about it. Yeah, you should be able to freely do that because, since it's a homework assignment, if you come across something that is, probably going to be done the next day or something like that, you should always go back and see what is the topic. It's a force on conductors, and everything is there in the e-textbook. Just go through those things, and then you'll get the idea very clear. Or I think even if you go for hints and stuff like that, you should be getting some ideas about force on moving charges, and then look into the e-textbook, and you'll get the idea, better ideas. So B, Q, V, sine theta is a force on charges moving in a magnetic field. So if you have a stationary proton, for example, in a magnetic field, what force will it experience? 0. That's stationary. So a stationary charge will not have any effect due to a magnetic field. But electric field, definitely it's going to be having effects. A stationary charge is going to be influenced only by electric fields, not magnetic fields. But a moving charge experiences If it is a moving charge, electrically you can deflect it, magnetically you can deflect it also. Both ways. Magnetically you can deflect it, electrically you can deflect it. Because you can apply a magnetic force on a moving charge, but you can't apply a magnetic force on a stationary charge. Electric forces can be acting on any charge, whether it's moving or stationary. Get it? It can act on anything. All right. So let's say we have a magnetic field in this place like that. Suppose you have a magnetic field going into the board. Suppose you have a magnetic field into the board in that region, and I shoot an electron into it. If I shoot into it an electron, so the electron is going to be shot into it. As the electron enters the magnetic field, will it experience a force?
Yeah.
Which way?
Down.
Now remember, we are talking about electrons, so before you use this left-hand rule, remember that this is the direction of current and not the direction of electron flow. So the moment you're given electron going that way, immediately understand that is like current in this direction. So put the current in that direction and then switch the magnetic field inwards. Which way is it? Downwards. So this electron is going to be subjected to a force, which way? Downward. So it's going to experience a force downward. How much? B, E, E. This is going to experience a force equal to BeV. Same thing as BQV, but this is specifically electrons, so BeV. So the force is experienced as BeV. It's the same as BIL thing, but we are just using the same, everything is same. The only thing is, when a charge is moving in a magnetic field, it is like a current, depending on whether there's positive charge or negative charge. So if it is electrons going this way, the current is going that way. If protons are going this way, then that's flow of current also, right? So if I tell you a positive ion is going this way, then you take that as the current direction, because positive charges move with the current. Negative charges move against the current, right? So keep that in mind. So when you kind of think about it. So yeah, the direction of the magnetic force is going to be this way. What will happen to the electron then? It will deflect. So definitely it's not going to go straight anymore. It's going to turn. It's going to turn. So after some time it's here. It's deflected.
Good job.
It's deflected. Now what do you know about the speed? At what speed will it be probably moving? Will it be the same speed, or will it have accelerated?
Same speed.
Why same speed? Isn't there a force acting on it? Isn't there a force acting on it?
Yes.
Then why is it not going faster?
Because it's like there's no change in the force this way. It's only changing the force.
So in other words, there's no component of the force in that direction. Another way of looking at it is, this force is perpendicular to the path. So what is the work done by a force when the displacement is that way and the force is perpendicular? Zero. So this force is not going to do any work on the electron, which means the electron is not going to gain any kinetic energy, because no work has been done, right? So the electron will still be moving at the same speed. So whatever speed is here, it's moving the same speed. Now which way is the magnetic force? Now it's going this way. Which one? It's like this way. BeV again. So the force is going to be perpendicular to the path. And when this electron moves here, it's moving that way. Which way is the force now? This way. BEV. What's going on here now? Centripetal force. Good. So basically what's happening is this electron is going around in a circular path, and once it comes here, it should shoot off straight, because once it is out of the magnetic field, nothing to turn it. So you can see this electron is describing a circular path. The centripetal force is provided by the magnetic force. The centripetal force is provided by the magnetic force. The centripetal force towards the center is provided by the magnetic force. So definitely the electron is going to describe a circular path. Not necessarily a complete circle, but yes, it is describing a circular path. Of what radius? Of radius r. It's going to describe a circle of radius r, such that the centripetal force needed is provided by the magnetic force. Now the centripetal force needed is mv squared over r, you know that equation. And what's the magnetic force? Is BEV. Right? Centripetal force is BEV. You can cancel off one of the V's, because that's V squared on this side and V on the other side. So finally we have that. And if you make R the subject of the equation, R is equal to mv over bq. The radius of the turn that this electron is going to take, oh, it's supposed to be BE, but I'm just generalizing it now for any charge. Okay? Yes, it's supposed to be mv over BE if you know it is an electron. But if you don't know it's an electron, it is a charge, then take it as BQ. So this is a general equation for the radius of the turn taken by a charged particle moving in a magnetic field. Make sense? The radius of the turn taken by a charged particle of charge Q moving with a speed V, having a mass m in a field B, is mv over bq. Now if I take this electron and shoot it from inside the magnetic field itself, like I take it to the field and then shoot it, then what will happen? If I shoot an electron that way, it just keeps going in circles. Because the force that is acting on it is perpendicular to the path, and so it will keep changing its direction because of that force, and it will just be in circular motion, right in the same spot. Now, gravity can bring it down, because gravity acts on the electron too, although it is kind of very weak. But the strength of the field and all that is much, much more compared to the gravitational field. So, technically, this is what is going to happen. It's going to keep circling the same place. Yeah.
Is it going in a circle on like a plane, or is it like
Plane.
It's not corkscrewing.
I will talk about it right now. It's going to just go like that. Now coming to his point. Instead of shooting it straight like this, perpendicular to the magnetic field, if I shoot it like that, at an angle. Now this velocity has two components, this component and this component. So this component will make sure it's going in circles. This component will make sure it's going laterally. So if I shoot an electron straight like this, perpendicular to the magnetic field, it will stay in the same spot and move around. But if I shoot it like that, then it will spin and advance same time. So it's basically like coiling forward. Make sense? It just coils forward. It's not going to stay in the same place. It just coils forward and goes on. Like a slinky kind of figure. So that's what happens if it is coming at an angle. Okay? Many of the natural things that you see, they're all due to this. Charged particles moving in a magnetic field. You can see it in your e-textbook. Yeah. All right. Okay. The radius depends on what factors can also be seen here. If the projected particle is heavy, then it will make bigger circles, right? Wider circles. Radius will be bigger. What if you shoot it faster? Bigger circles. What if you are shooting in the magnetic field which is extremely strong? Smaller. Right, Alex? That's going to be smaller. What if it is doubly charged or triply charged? Then it's going to be smaller also. Like instead of singly charged dust particles, if it is doubly or triply charged, more charge, less radius. Okay? You want to? All right, next. Mass spectrograph. Have you heard about mass spectrograph before? Kangda. What's a mass spectrograph? Mass spectrograph. Did you get up at all?
What?
Did you stand up and walk around? I gave you a break of 2-3 minutes and everyone was like talking a lot and all that.
You must have been sleepwalking and didn't realize
I mean, that's the best part, yeah. Because as soon as you all sat down, I see that he's out already. I said, that's not possible. That's not possible.
Mass spectrograph.
All right. Yeah, mass spectrometer. When did you hear about it last? Chemistry. What does a mass spectrograph do?
Finds the mass.
Say it again.
Beer's law, absorption,
Absorption.
That's the light.
You're talking about spectrums, emission absorption spectrums? No.
No.
Does help find the mass of certain particles.
Basically, it's to compare the masses and charges of particles. That's what the mass spectrograph is supposed to be. Mass spectrometer, mass spectrograph. There are different varieties of mass spectrographs. One method of mass spectrograph is called the Bainbridge mass spectrograph. Bainbridge mass spectrograph. So, what is needed? We need charged particles, and we need them moving, and we need to subject it to magnetic fields because you know the radius is mv over bq, that equation. So if you want to compare the masses, you can compare the radius. If you see the radius and compare with the masses, that's how it is compared. So it's basically a study looking at the radius and looking at, but then we have to keep some other stuff constant. We have to keep some of the stuff constant, otherwise you can't do it. So how do you produce charged particles? How do you get charged particles?
Electric fields.
You can do by anyway. I mean, like you can actually produce charged particles. Basically means ions. So I can have some dust particles, and I can charge them by friction, right? Or I can just scoop some of this electrons right now. I scoop some of them. Electrons can be scooped so easily. That's why when you remove the jacket, immediately you get charged. The jacket gets charged because of that frictional part. And remember, when you do that, you're taking millions of electrons. It's not like small number of electrons. It's like not one. It's a lot of electrons that are coming out because its static charge that you're talking about is strong enough. Strong enough to create a current to damage stuff. So let's come back to this mass spectrometer. So how do you scoop these electrons? How do you create charged particles? You can create charged particles by radioactive methods. You know, if you send some radiations onto some particles, it can get stripped off the electrons and so can get ionized. Right? You can get charged particles that way. You can get charged particles by heating, just by heating. If you take a metal plate and just heat it, because of the agitation that's taking place inside, the free electrons kind of bounce off. They just come off. And those are called thermionic emissions, thermal emissions of electrons. Like heat it and make it come out. Okay? And that's pretty much what was done in the cathode ray tubes. Have you seen cathode ray tubes? The big televisions, the big bulb televisions. What is in the very back? In the very back is a filament, like that. It's a heating coil. And what is next to that is a plate. So as soon as this gets heated up, the plate gets heated up, and the plate starts spitting out electrons. It just kind of releases electrons. Now, once the electrons are released, you want it to go faster. All right, so this is the cathode. And then there is a cylindrical anode. They put an anode here and connect a potential difference between these two. Now what's happening? The electrons are released, and these electrons are going to accelerate into this, right? And the electrons accelerate and come through the middle. It's like it's hollow. And as soon as they pass by, because once they come inside, it is in a equipotential region, and so it won't get attracted anyway, just like goes straight. So once it jumps out from here, it's going to go with a certain speed. And this whole thing is called electron gun. This assembly is called electron gun. So the first part of the picture tube, this part here, is the anode and the cathode and the electrons, the filament. This is the first part. That is the electron gun. And once the electrons move out of this gun, then they come and strike the screen. Now, instead of making them go strike the screen, you can actually deflect them up and down electrically or magnetically, any way you want. So the electrical signals that needs to be displayed on the screen is sent into those deflecting plates. And then you can get the picture on the screen. So the cathode ray tubes function is what I'm trying to explain here. But what's the main brain behind it? The electron gun. The assembly that actually produces the electrons. So when the electrons come and strike the screen is coated with a fluorescent material. And that is why it actually kind of brightens up the screen. When electrons come and strike, the screen becomes bright. Again, we'll talk about that later on. So this is cathode ray tube. So we have an electron gun which will produce some speeds. Now, will all the electrons come out with the same speed over here? Not necessarily. Because some of them, when they come out from here, they're already moving fast. And then you accelerate them. Some of them, they just barely get released, and then they get accelerated. So which means what? Whatever comes from here is going to be having different speeds. Correct? They move with different speeds. So, but we don't want that. We want particles to go with one speed. So how that is achieved? All right, the first part of the mass spectrograph is the charged particles. Charged particles are either produced from elsewhere and brought in, or suppose you want to investigate the ions for chlorine, right? So we got 17Cl35 and 17Cl37, the two isotopes. You know what I'm talking about? Yeah. So different isotopes are there for different different substances. So if you want to investigate it, you want to ionize that particular gas, say chlorine, and then bring it here. And you want to accelerate them. Only then they can acquire speeds. To accelerate them, we have to accelerate these from a cathode to an anode. And so these charged particles will speed up. So what is applied between these two is a potential difference. What is applied between these two is a potential difference. So when a potential difference is applied on a charged particle Q, what will happen is they will start moving faster and faster. They get accelerated. And when they get accelerated, when they come out from here, they will move with a certain speed v. How can you get a relationship between the speed and the potential difference here. Okay, what kind of energy is it gaining? Kinetic. Half mv squared is the kinetic energy gained. How did it gain it?
Potential energy.
What is doing the work?
Electric potential.
Electric potential difference is doing the work. How much is the work done by potential difference to move q coulombs? Formula? VQ or QV. So the work done electrically is QV. Electrical work done is QV. And this is what is acquired as speed, as kinetic energy. Now this V is capital V is potential difference, and this is speed. So how fast are these electrons moving, and how fast are those charges moving there? The speed with which the charges are moving there can be seen from here. It's 2qv over m square root. Is that okay? If you make small v the subject of this equation, you get v is equal to cross multiply 2qv over m square root of it. So this is the speed with which the charges are going to come. And that is if these particles were initially at rest. But if they're already moving, then these speeds are going to be different, right? So this half mv square I wrote over here is basically the change of kinetic energy. So if it already were moving, then the speed is definitely going to be different. Like that means you will be having a bunch of ions or charged particles coming through here, and they will all be moving at different speeds. They will all be moving at different speeds. So this is the first part of your spectrograph. So by discussing about the first part of the spectrograph, you get to know this equation. How fast are the charged particles going to move after accelerating by potential difference of v volts? Here is the equation. How did that come from here? I think we have discussed this in potentials chapter, right? This one. Okay. So now we have a bunch of charged particles moving from here, but they all have different velocities. But now we don't want all velocities to go through. We want only one velocity. We want to screen, we want to filter these people from here. We want to filter this in such a way that I want only a selective velocity to go through. I don't want all of them to go through. Make sense? So this is the electron gun. This is the accelerating part of it. And then the next segment over here is called the velocity selector. We can select specific velocities. How? As these particles are moving like this, as these particles are moving in the different speeds, different velocities, they're going to go straight. Well, there are other stuff that I'm not drawing here, like grids or slits, so that these can actually sneak through, right? In one, it'll be more linear, sort of. Now, if an electrical plate is attached here, if you put two plates electrically, and let's say these are positively charged particles. No, yeah, positive, negative doesn't matter. Let's say they're positively charged particles, and you're applying a potential difference, negative here and positive here, so you want to accelerate them. You want to accelerate these, you need to apply negative on this side, positive on this side. So you need to apply a potential difference of negative, positive, right? So you can get it accelerated. Now, you have two plates over here, and what's coming in are positive charges, right? Suppose I apply to these plates, if I put plus here and minus here on the plates, what will happen to these positively charged ions? Which way are they going to get deflected? Upwards. They're going to get deflected upwards. So these are going to be deflected upwards. Are they all going to come out from the same place? Yes or no? No. Because we don't know. They're all coming at different speeds. So the slower ones will land here earlier, right? The very fast ones will be barely deflected. So these are going to be sprayed off like that. So anyway, one thing is sure, this is going to be deflected. It's going to be deflected. So if I'm going to apply a field E, if I'm going to apply a field E, and if I'm going to apply a magnetic field B, I'll come to the magnetic field later, but if I'm going to apply an electric field E, and these are the positive charges which are moving here, what force will these positive charges experience? What's the formula for force in a field? Yeah, EQ. So the force that is acting on these charged particles in that direction is QE, simple. You get it? Now we'll talk about the magnetic field. I want to apply a magnetic field here in this region so that these positive charges are going to be deflected the other way. I want them to deflect the other way. So which way should the magnetic field be applied? Because it's up to us to apply the magnetic field. So these are positive charges. If they are moving like this, which way is the current? Same way, right? These are positive charges, so if they are going this way, that means the current is the same way. So this one is going to be that way. Now, if I put a magnetic field in, which way are they going to get deflected? Up. But I don't want it to get deflected up. I want it to go down. So I need to apply a magnetic field outwards so that they can get deflected. So I'm going to apply a magnetic field around here, out of the board. Make sense? So this is a magnetic field I'm applying in this region, out of the board. So what's going to happen now? If I put the electric field on, it will deflect upwards. If I put only the magnetic field on, it will go downwards. Now if I turn on both, now two forces are going to act on them. Electric force is acting, trying to deflect them that way. So on the charged particles, the electric force is going to be pulling it that way, and the formula is QE. Magnetic force is going to be pulling it downward. Formula is
QE.
BQE. You just saw it. Magnetic force is BQV, downward. Now if QE is equal to BQV, what will be the deflection? None. So if that happens, then you're getting a single velocity to go through. Only one velocity will be able to sneak through. Because I can actually put some filters here. I can put some filters here so that anything that comes right in the middle can go out. Anything that goes on the other sides and all that, they'll get absorbed. So QE is equal to BQV. Q is gone. So it doesn't matter whether it was doubly charged or triply charged, they'll all be able to go through if the velocity is E over B. So this is called the velocity selector. This combination of magnetic and electric fields together is called the velocity selector. Make sense? So going back here, this is the region where charges are accelerated to different speeds, but we don't want different speeds to go through, we want only one speed to go through. And so we need a velocity selector, and we got this velocity selector by imposing a magnetic field and electric field perpendicular to each other. See, magnetic field is out of the board, electric field is upward, right? So when you apply magnetic field and electric field perpendicular to each other, these charged particles will get sprayed all over the place like that, and some going that way, some going this way, some going this way, and but very few will go straight, and those are this. So if you know the electric field and the magnetic field, you know how fast they're going. So V is known. You understand what I'm saying? You know what is V, because if anything is coming through here, they must have a velocity equal to E over V. Because you applied E and you applied the B also, and you see that these are coming through. That means these have a selective velocity, which is E over B. Now that the velocity is selected, you need to now compare the masses. And for that, what do you do? I'm taking this off. For that, what you do is we want to turn this. We want this to turn. Let's say I want to turn it this way. Which way should the magnetic field be applied? Because we have to turn it. Same as this. Out. Right? So, in this whole region, I'm going to put a magnetic field out of the board. That's a totally different magnetic field. Remember that. This is not the same as B. This is B prime. Something different. So now I'm imposing a magnetic field in here. What will happen to these particles? What will happen to these as they enter? They'll get turned into a circular path. So this will turn into a circular path. And over here, we put a fluorescent screen. That's a screen. That's a fluorescent screen. So what will happen to these charged particles? They'll come and hit there, and it will produce brightness. Or you can put a photographic plate. So, send them, take a picture, analyze the picture. Both can be done. They're going to come here. What's the radius of the turn that is taken here? What's the radius of the turn? mv over bq. You just saw it earlier. The radius of the turn taken is mv over bq. Velocity, fixed. We selected it. So we know what it is. This velocity, this is now b prime q. That's a different b. What is turning over here is a different magnetic field. So this is fixed. So the radius of the turn is m e over b prime q. I just substituted for velocity there, right there. Now look at this equation. That's radius. Radius is proportional to mass and is inversely proportional to the charge. Both these are constants. All of these are constants. So R is proportional to the mass to charge ratio. That means, I'm just asking one more question here. If I send a chlorine 35 and a chlorine 37, which one is going to hit here? One of them is going to hit here and the other is going to hit here.
The heavier one's going to hit the rest.
That's good. So the heavier one is going to hit here, the lighter one is going to hit there. So you can compare the radius and then do measurements.